All right, we're going to take a look at the gas laws, but to do that we need to look first of all at the work that Lord Kelvin did. He discovered that when gases are cooled, their volumes decrease. And he took some really precise measurements and discovered that essentially the volume decreases by a factor of 1 over 273 for each degree Celsius that the temperature is decreased. And if you extrapolate that, you get down to a point where volume equals 0 at about minus 273 degrees Celsius. And so that's kind of where he figured molecular motion would theoretically cease altogether. And so he developed the Kelvin temperature scale, which is simply the temperature in degrees Celsius reduced by 273. 0 degrees Kelvin then is at minus 273 degrees Celsius. 0 degrees Celsius then is 273 Kelvin. Now today we've got a little bit more of a precise value on that, 273.15, and there's a whole bunch more decimal places now. I think we're down to about 15 decimal places in terms of the precision, but we're going to use this value here, 273.15, for our calculations. All right, so Charles' law. This is the second of the gas laws, and we're going to basically use the relationship between volume and temperature. And so what Kelvin discovered is that what Charles discovered was that it's directly proportional to its Kelvin temperature. So the direct proportionality then leaves us with a relationship of V over T being constant all the time. That, of course, gives us the relationship V1 over T1 equals V2 over T2. And you can see right away that if we use our Celsius temperature scale, and we happen to use the freezing point of water, we run into an issue of dividing by 0. And that creates a problem. With normal temperatures, we don't usually get down to absolute 0. In fact, nobody's quite gotten there yet anyway. And so we've gotten close, but not quite. And so what we have is we have to convert this temperature always to Kelvin rather than degrees Celsius, so that we don't run into that divide by 0 issue. All right, so here's an example. A balloon is filled with helium gas to a volume of 1.2 liters and a pressure of 105 kilopascals, temperature of 15 degrees Celsius. The pressure remains constant. The temperature rises to 303 Kelvin, what will be the new volume of the balloon. All right, so again, let's pull out all the information we have. First of all, the T1, initial temperature, 15 degrees Celsius. We need to convert that to Kelvin. I'm just going to drop the 0.15 at this point, just for example. In your calculations, you will use this 273.15. So that gives us 288 Kelvin. Your T2 is already 303 Kelvin. That's fine. Initial volume is 1.2 liters. We're going to solve for V2, and we should get 1.26 liters. All right, so again, make sure that your temperature units are the same. Make sure your volume units are the same. Other than that, everything is fairly straightforward. The math is not hard. All right, so try these questions. You like my animation? I like my animation. Anyway, bring questions to class. We'll talk about it there.